house today. And I guess, Cumrun, you should see that as a compliment. So come often so that we fill this hall. At any event, we just heard an excellent colloquium by Cumrun Vafa, who knows our language despite the fact that he's a string theorist. That's quite amazing. He speaks our language and makes predictions that can be tested, and in fact passed some observational tests. So that's testimony to his to him being a real physicist. Thank you, Cumrun. But before Cumrun, I just want to mention a few other. I just wanted to mention also that next week we don't have an ITC lunch. It's Thanksgiving, and I wish everyone a wonderful holiday. And we will meet for the last session of the ITC lunch 2 weeks from now. So the other speakers today are our own Ralf Konietzka, a graduate student in our department, astronomy department. He will speak about ray tracing fast radio bursts through IllustrisTNG. So basically, he's doing simulations that have implications for fast radio bursts, which is quite interesting. And then we'll hear from Anirudh Chiti from Stanford, right here, who will talk about uncovering the ancient Milky Way with DECam magic survey. And finally, we'll hear from Isabel from Caltech, and she'll tell us about the Galactic Center gamma ray emission in MHD galaxy formation simulations with full cosmic ray spectra. Thank you. So we'll start with Cumrun. Go ahead.
Thanks, Avi, for inviting me here, and it's a great pleasure.
Could you get the microphone again? Sorry.
I need a printer, huh?
Yeah.
It's recorded, that's why. Anything you say can be held against you.
Okay. So it's a pleasure. It's a pleasure to be here, and I just gave a talk. So what I'm going to say in these short 10 minutes is basically a quick summary of that talk. Hopefully it's not too boring for the ones who already were at the talk, but yeah, it's a review of the talk. So one of the features of, what is the area I work on in string theory, and the main aim of string theory is to try to explain quantum gravity. And in the midst of doing this, we have found that it does that, but it also gives us very, very special types of particles that we see and so on in those theories. So we have different examples that we get in string theory, but we don't seem to get everything that we could order. Like we say, I want this force, I want this set of particles, and so on. Can you write down a string theory which gives me these? The answer is, for almost everything you give me, I cannot give you a string theory. And in some sense, it's actually not a failing of string theory, but actually a feature of quantum gravity, we believe. We believe gravity is not consistent with infinitely many possible choices that might otherwise look perfectly normal. Having a UV completion of gravity, quantum completion of gravity, puts a huge amount of restriction, basically cutting down an infinite set of possibilities to a finite set of allowed theories. And that is basically the main surprise that we have found in string theory, is this feature, that the number of quantum gravity theories seem to be finite, unlike field theories. So what I'm going to tell you today is the following. So in string theory, we have found the following features. If you have a small parameter in your theory, like coupling constants and sizes of the universe, extra dimensions of the universe, and so on, they always turn out to be related. That if you go to the extreme regimes, you can interpret them as larger extra dimensions, as if the parameters can transform and represent some number of dimensions opening up and getting bigger and bigger. That's the dimensions in addition to the 3 dimensions we are talking about, which are big. So in string theory, we have some extra dimensions. And whenever your parameters in 3 dimensions, 3 plus 1 dimensional physics, like coupling constant of electrical coupling constant, or masses of particles, or some other parameter, when those in your theory become extremely small or extremely large, what we found happens in string theory is that some of the extra dimensions are becoming large. So that's the feature, that there's a correspondence with parameters being small in your effective four-dimensional physics and the extra dimensions having something getting large. And moreover, we find that whenever there are larger extra dimensions, you always get a weakly interacting light tower of gravitons. What does that mean? Well, just it's kind of intuitive. That is, if you have some extra dimensions opening up, from the perspective of lower dimensions, you have to choose harmonics of solving the solutions to the Laplace's equation for the graviton in the internal dimension. When that becomes bigger and bigger, you have long wavelength solutions, which are light. So the more and more bigger and bigger the space is, the modes of the graviton become lighter and lighter. So large extra dimensions means a tower of light graviton towers in particular. So like kind of standing gravity waves. Okay, so what does this have to do with what I'm going to talk about today? It has to do with the unification of dark sectors. I claim that this simple set of ideas lead to a picture which connects the dark energy and dark matter together. Namely, the small parameter in question is the dark energy itself, or cosmological constant, we sometimes call, which is in fundamental units in physics 10 to the minus 122. This is very small in the fundamental units. So therefore, we are in the category of small parameters. So string theory immediately says, oh, if you're in that category, you better look for some larger extra dimension. In this case, we can use this combined with some other experimental observation to predict that not all the extra dimensions are large, but just one of them. And that one extra one has a scale set by lambda itself. Dark energy is energy per unit volume. So if you convert it to energy units, it's energy to the fourth unit. So if you take lambda to the minus 1/4, it gives you a length scale. So the dark energy gives you a length scale. That turns out to be related to this micron scale. So what we are saying is that the dark energy predicts a scale of this extra dimension, which is a micron scale, a reasonable extra dimensional scale. And we said that there is the ingredient here, which is weakly interacting like graviton towers, which is still here also, but then we can interpret this tower as dark matter candidates. In other words, the dark matter could very well be the graviton modes in this extra dimension, and it automatically solves the problem that is not observed easily. It is gravity. Gravity is not easily detectable. So all the direct detection experiments for dark matter are doomed to failure if our picture is correct, because they are purely gravitational. And we don't have to make up a candidate. It's just graviton. Graviton is there. We didn't have to introduce a new series of particles or stable this and that. It's just the gravity itself. So the only feature is this extra dimension, which is the bread and butter of string theory anyhow. So we didn't have any extra ingredient. We just used the string theory ingredient, and automatically it gives us this picture. So the picture we are led to is that we have our universe, which is visible matter, the galaxies and us and all that, is stuck on a 3 plus 1 dimensional subspace of a 4 plus 1 dimensional universe, where the fourth direction is what we call the dark dimension, micron scale. And the dark matter should be viewed as perpendicular KK graviton modes, which are living in the fifth dimension, in the fourth dimension, sorry, the dark dimension. So the size of the extra dimension turned out to be not easily stabilized. In string theory, it turns out whenever the energy is positive, it kind of wants to roll. So if you think about phi as parameterizing the radius of this extra dimension, we're expecting that if you want to have v of phi to be positive, then it ends up naturally that v prime is also not zero. That is, the slope of it is typically not zero. And moreover, if that's the case, if phi radius is changing, the dark matter mass is also changing, because it's just a familiar redshift thing that we all know in astronomy, that if you have, in cosmology, you have a universe expanding, the wavelength redshift. This is true also for the extra dimension. If the extra dimension is getting bigger or smaller, the matter goes up or down. So there's going to be the mass of the dark matter will also be scaling with phi. So we have one field here, phi, which is parameterizing the radius, for which both the potential, which is the energy in the universe, which you can associate with the energy of the phi field, and the mass of the dark matter will be parameterizing it. So string theory results lead to the surprising result that I'm going to tell you about. That's a paper we wrote with my colleagues in 2019. The question is, what is these slopes? And the prediction is, in string theory, these slopes, V prime over V, or M prime over M, is basically given by order 1 numbers, C and C prime, divided by M Planck. In other words, the value of the slope is also set by V. And the value of slope of the M with respect to phi is also set by M. Up to order 1 numbers we cannot determine from theory alone. That is a surprising prediction from the string theory perspective. So that means that V prime is also of the order of 10 to the minus 122 in our universe in fundamental units, because we are saying V prime is of order V in Planck units. So the V prime is of order 10 to the minus 122. So therefore, it's almost flat. That means it's very easy to confuse the dark energy, for example, with constant cosmological constant. So we are expecting it to be a very fine effect. So the very fact that it hasn't been easily observed is consistent with this prediction. It should not be easily observed because the slope is also small as V itself. So this paper we wrote in 2019 tried to explain why is it possibly consistent with observations at the time that the dark energy seemed to be constant. We could say that, well, it's expected to be very small. Anyhow, the slope and this one. And so this is a very simple model in which you have a 2-parameter model locally given by C and C prime, 2 constants of order 1, and you can see how it fits with the data. So thankfully, the recent results, in particular by the DESI team, seem to find evidence for evolving dark sector. And so then it's natural to just look at our model in 2019 and fit it to the data and see what values do we get for C and C prime. So if we do that, so this is the results of the parameterization of what is called the CPL parameterization, where parameterizes the equation state of dark energy with respect to a value of it double is 0 and the slope of it WA with respect to varying of A. And this gives you the significances. And the model that we are fitting here is a fading dark sector, which gives you significance very similar to the CDM, but avoids the phantom behavior that this model has. Gives you a very simple physical model, predicts the fifth force in the dark sector of order of 0.5% by the exchanges of the phi field between the dark sector, which is consistent with the observations which up to now was bounded to be between less than 0.2. And it gives you a prediction of the values which were order 1 indeed are order 1. C becomes of order 1, as you can see. These are the fits. Experimental fits are very close to 1, order 1, and C prime is 0.05. So that's basically what I want to say. I heard the ring here. Thank you.
So from a global point of view, we live in a false vacuum, right, in this case, and the scalar field slowly rolls down to the true vacuum, which may be 0.
Yes.
And in principle, you can get tunneling, right? So is the problem. There is this doomsday scenario that there would be some domain wall coming across us and kill us, right? Because the vacuum will decay to 0. What, in your picture, is that possible?
Well, that's more natural if you're in a metastable situation. In a metastable situation, the only way to get out of it is through this, through exactly what you say, the process of this bubble formation. But here, so that's one possibility. It could be that you are exactly in a metastable situation, even though it's not very natural in the context of string theory. More naturally, you would be rolling. If you're rolling, you wouldn't be decaying like that. So it's much more natural just to go down. The output for that, the instant calculations will give you badly suppressed, so that will not be the way to go.
If you look at the multiverse, there are many regions, each of them has a different.
Well, if you have one scalar field which is this radius, it's just rolling. It's just, for us, it's a very concrete model.
In our.
Yeah.
Right. Okay.
Kumar, is the C prime here the same C prime you said has to be order 1?
C prime, so if C prime is order 1, is the same C prime, except that you have to realize that when we say some moduli, some parameters are changing, the C prime is not the direction aligned necessarily just with the fifth dimension. Namely, the phi may be parameterizing a moduli, a shape of the universe, that could, for example, be shrinking in the thing and then elongating. projection of that direction to the fifth dimension is what we are measuring. So C prime is a projection of that C prime in the fifth dimension parameter. So there's a sine factor, cosine factor. I think if you take like, if you literally one of these, one is like 70 some degree angle will give you the 0.05. So it's order one in that sense.
You're sticking your neck in terms of making a testable prediction.
It's dangerous, I know.
No, so my question is, suppose, I mean, is there a chance of ruling out string theory?
No, I will tell you. Let me explain to you. So it is very unlikely that C and C prime U order one is completely random if it's indeed is in the case. So it won't prove string theory if this is observed. I would say it gives you circumstantial evidence because the model that we proposed in 2019 was at the time where it wasn't, and it gives you a model. Now, suppose it wasn't observed, so let me go to the reverse one. So you could say, oh, what happened? So suppose you find, I mean, it depends on what you find. Suppose you say, oh no, indeed the dark energy is not rolling, sorry, the dark matter is not, everything looks perfectly fine in Lambda CDM, so what would I say? So as I say, that in the context of the dark energy, there is possibility of metastable vacuum, whose lifetime is of order of Hubble times log factor. So that if we are in that situation, then you could have a longer lived, even up to a trillion-year lifetime. Not arbitrary, but trillion years. So that's a possibility. I cannot rule that out. But I would say that's still more natural to have this one. So I would say it won't rule out string theory. Even with the conjectures we are making, it won't rule it out. Because you could have either of those two. But I would say this is much more natural to have. But we don't know. I mean, I think the idea is that in theory we're just saying what is natural, and we can see if it fits the data, that gives you evidence for it. It won't prove it, it will give you more evidence. That's the way I view this.
Okay, Ramesh?
So this fifth force, the model predicts that it should be on the scale of about a micron, right? And it will have a different radial dependence. Instead of 1 over r squared, I think you said 1 over r cubed.
The force, the Newton's force.
The force itself.
Yeah, so I'm just saying that the Newton, so for people who weren't here, so the Newton's force law in three-dimensional space goes like 1 over r squared. If the space was three-dimensional becomes four-dimensional space, you'll be 1 over r cubed. Each time the dimension goes up, the power goes up. So what that means that if you bring points closer than a micron, you will feel the gravity leaks out to the other dimension, you will see that 1 over r cubed.
But there was
Right,
a confusion
so-
here because Ramesh was referring to the fifth force. And
The
I think
fifth
the
force,
fifth
well,
Oh, no, which one are we talking about? Sorry.
F5.
Oh,
No,
sorry,
no,
that was
that is
confusing.
big scale.
Not 1 over r cubed. No.
That is not 1 over r.
No. This is 1 over r squared. This is a massless. This is the usual massless exchange of a field phi between dark matter. So it gives you an attractive force like gravity, but for 0.5% the strength of gravity.
Yeah, so it means the equivalence principle is violated for
Yes,
dark matter.
in the dark sector
Dark
only.
matter relative to ordinary matter
Yes,
moves.
it's a long range violation of equivalence principle for the dark sector only.
So the dark sector has the normal gravity and
this.
a little bit extra,
Exactly.
so it will affect the dynamics.
Exactly.
Okay, which has testable predictions, I
Yes.
assume.
Yes. This would be interesting to predict. For example, the bound that was previously put, C prime was less than 0.2, by Kamikansky et al. Was based on the tidal disruption of Sagittarius when it came close to Milky Way, and that if there was a fifth lack of equivalence, if the equivalence principle was violated, you get tidal effects, and the lack of observation put a bound that was C prime is less than 0.2, which is what I was quoting. So this will have effect. So if we have 15 times more sensitive observations, I would expect there to be able to be seen.
Well, it's interesting also to test systems like the bullet cluster, because if the dark matter
Yes.
has extra force, the motion relative to
Yes.
Yeah, right.
Yes, there should be a whole host of it. So we are now predicting a fifth force. I think that's probably the most exciting one. I should say that the fifth force portion is predicted based on DESI data alone. You don't need the supernovae data. So just the DESI data by itself predicts this value for us. So whether or not the dark energy evolves, whether V is evolving or not, will be determined by supernovae data. But whether the dark matter is evolving, I claim, is already good evidence from the DESI data.
Thank you so much, Cumrun, and we will try to test your theories.
Yes, thank you.
All right. Can you all hear me well? Perfect. Thank you so much for having me again. My name is Ralf Konietzka. I'm a PhD student here at Harvard, supervised by Lars Hernquist. And today I will be talking about fast radio burst cosmology. Let's jump right in. So we are having our fast radio bursts here on the left, and they are sending out a plane parallel radio pulse that then, as the pulse interacts with the free electrons along the line of sight, gets more and more dispersed. And the amount of dispersion shown here tells us how many electrons there are along the line of sight between the radio burst and us. So the so-called dispersion measure gives us a measure of the surface density of baryons between an observed radio burst and us, the observer. And we can decompose the dispersion measure in three main parts. The electrons that are residing in the host galaxy of the radio burst, we call it DM host. Then all the electrons coming from the IGM in between, the cosmic web basically. And then the contribution of the CGM and ISM in our Milky Way galaxy. And in this talk, I will mainly be focusing about the cosmic dispersion measure, and we will be using the IllustrisTNG simulation suite to study them in detail. But before we jump into TNG, let's simplify the picture a little bit. So we use a perfectly uniform universe from now. So all the baryons are uniformly distributed, and we look at different directions on the sky. As I said earlier, this dispersion measure here gives you a measure of the surface density of electrons. So the deeper and deeper you integrate in Redshift, the more and more electrons you accumulate, and so you get a monotonically increasingly function as a function of Redshift. If instead in our universe all the baryons were located in the halos, we had some lines of sight that basically go through no halo at all, so we get this lower limit of our distributions, and other lines of sight go right through the densest parts of the halos, corresponding to this upper tail. And in a more realistic universe, we have somewhat a mixture between IGM and halos, so we get a much narrower distribution. And the question now becomes, how does this look like in the TNG universe? And for the rest of the talk, keep in mind that the main part, or the important component that we would like to study of this distribution is not its mean evolution. The mean is mainly given by the cosmological parameters of the universe. The key observable is any of the higher moments, so the variance, skewness, kurtosis, and any higher. Because they include where the baryons are located in our universe, and with that, how strong or weak the underlying feedback prescription is. So now I will walk you through how we can retrieve dispersion measures not only from a single snapshot, but then also going to higher and higher redshift. But for now, let's start with a single simulation snapshot in TNG. And for that, we should recall that TNG is run on a so-called Voronoi tessellation that I'm showing you here with its mesh-generating points shown in orange. And all the Voronoi cells in the TNG suite have sizes spanning of a few tens of parsecs up to a few hundred of kiloparsecs. What people usually do in the literature, they map this tessellation onto a Cartesian grid. And through this mapping, you usually average over the densest parts of your cells, and with that, lose information. We instead construct all the line segments along a given line of sight, shown here in blue, and retrieve with that the full information of the underlying Voronoi grid. And to do so, we use a key feature of the Voronoi tessellation, namely the following. If we have two neighboring cells with their boundary, where they're basically having a boundary plane here shown in blue, then the plane is exactly constructed by the plane that separates the vector that spans the mesh-generating points, separating this vector into half. And this gives you the boundary plane. And we can use this unique feature of the Voronoi tessellation to then construct all the line segments along a given ray. So we first identify our starting and our end cell, and with that, their mesh-generating point. Then we construct this orange vector and the corresponding plane that splits the vector in half. And if those two blue cells were neighboring cells, then this plane here would be the boundary plane between the cells. Since this is not the case, we know for certain that there has to be an additional cell on the line of sight. We can identify the cell and then continue this algorithm recursively. So we construct two new vectors, two new planes, and identify two new cells along the line of sight. And now we are in the regime where we have neighboring cells, meaning in the next step, we find planes that are exactly the boundary planes between two neighboring cells, and this is the moment where the algorithm knows it has to stop. While on the other hand, here in the left hand of the picture, we have to go one step further to then identify the last cell in this little schematic picture. So in other words, we have now a method to reconstruct for a single simulation box all the information of dispersion measure in the perfect manner. So we get all the information, don't have any artificial additional biases. And we would like to extend this now to higher and higher redshift. And what we do here is we introduce the so-called continuous ray tracing method, where we stack several simulation outputs along each other, keeping their orientation the same, such that we can use the periodic boundary conditions of the simulation and then shoot tilted rays through those boxes in order to avoid that we go through the same over or under density several times. So imagine if you would go plane parallel through the stacking, then you would always trace through the same galaxy over and over again as you go through the same snapshot again. And this is in contrast to what's currently done in the literature, where mainly due to computational reasons, people output the dispersion measure for single simulation snapshots and then interpolate between those snapshots using the trapezoidal rule. This method gives you the mean correctly, but any higher moment will become distorted. And the reason for that is that this interpolation method based on the trapezoidal rule will not basically model your cosmic variance correctly and then leads to this distortion. In the actual paper, we test several other methods, and if you're interested in more methodology, please come and speak to me afterwards. For now, I will just concentrate on these two methodologies. And if we compare them in terms of their PDF, it's several redshift output, 0.1, 1, and 3, that then we see the trapezoidal approach is distorting heavily the PDF compared to our ground truth continuous ray tracing approach. To make this more quantitatively, if you look at the 4 first moments, as I said earlier, the mean is always reconstructed correctly, but the standard deviation in the higher moment is heavily distorted by over 50%. So if we would like to compare our observed FRBs with the simulations, we really have to make sure that we don't have these artificial biases in our numerical results, because otherwise we would bias our basically drawback from what we learned from the observed FRBs in the wrong direction. So to wrap up the methodological part, we have now a knowledge how to construct dispersion measures in TNG in an unbiased way below the 1% limit. And with that, we can construct these beautiful dispersion measure maps on the full sky. And here we look from a Milky Way-like environment. So this galaxy here corresponds to an Andromeda-like galaxy, and the big halo here on the right is a Virgo-like cluster. So if we instead evolve this map as a function of redshift, we see how the Andromeda analog pops up. And then at around 70 megaparsec, we see the Virgo cluster coming into the field of view. And the deeper and deeper we go in redshift, the more the cosmic web gets imprinted in our full dispersion measure map. So with this map now, we have all the tools that we need to look at the question that I posed in the beginning. How does the dispersion measure redshift relation look like in a TNG-like universe? And now this distribution that I'm showing you here is accurate on the percent level, since that all the systematics that would come through the different methodologies are reduced below the percent level. And you can see here wonderfully the so-called DECam cliff, which is determined by the least amount of baryons in the cosmic voids, and then the higher outliers, which are given by foreground halos that are crossed by the lines of sight. And if we now would like to compare this to the actual FRB observations, there's one little step missing. Let's go back to the introduction where I said we mainly concentrate on the cosmic dispersion measure. So we are missing currently the Milky Way dispersion measure as well as the host. For the Milky Way, we have a fairly well understanding from local pulsar measurements that we can basically calculate out. However, for the host, we again have to rely on simulations. So what we do next is we populate our simulation with FRBs, in this case tracing star formation, assuming FRBs come from a fairly young stellar population like magnetars. And then we can combine our host measurement with the IgM measurement and the Milky Way measurement to then have a comparison between observed FRBs and simulations. And this is what it looks like. So I'm showing you here in redshift versus dispersion measure, again, surface density of electrons, the observed FRBs in red, and in blue, the distribution given by TNG. And on the 1 sigma level, it seems like the observed FRBs agree well with the output from TNG. However, if I plot the 1 to 99th percentile, it seems to become apparent that TNG, the distribution is too wide, meaning there are too many baryons located in the halos, and the distribution within the halos might be too peaky. To look onto this picture from a different angle, we can also compute for all the single observed FRBs the 1D PDF, get from there the percentile, and then plot basically a percentile plot in a 1D view. If we do so, then we see here as a function of the fraction of observed sources, the observed percentile. So if we had a perfect one-to-one correspondence between simulation and observations, we would get this black line. However, TNG seems to underpredict the percentiles, meaning the distribution is too wide. There are too many baryons in the halos, or in other words, the feedback might be too weak. So we can now ask the question, how does this picture look like if we use a stronger feedback, like in the old Illustris run? So we would expect this curve to be shifted up. And it seems that Illustris is very heavily over-predicting the observation. So we have no attention between Illustris, TNG, on the observed FRBs, and this fits well in a picture of recent observations of the KSC effect on X-rays that also seem to imply that the feedback implementation with that, the distribution of the baryons in the TNG and Illustris model is slightly biased either in a high or low way, and then the next generation cosmological simulations need possibly a mixture model of the two between TNG and Illustris. And with this, I conclude, and I leave you the QR code to the paper and the QR code to download all the catalogs that I presented, and I'm happy to take questions.
So, Ralf, these simulations are based on the assumption that the UV background is uniform.
Yeah.
And in reality, well, we know of two reionization epochs, one of helium by quasars and the earlier one of hydrogen. And obviously, if you go to those redshifts, you will see you could actually map how the evolution of the intergalactic medium. So that should not fit your simulation, right? It needs a different simulation with the radiative transfer.
That's correct. So the model for helium and hydrogen ionization, those simulations, is too simplistic to really get what you're looking for, correct reproduction of the helium or hydrogen ionization.
So you can do it in your postdoc years after you finish your PhD.
But one possible example would be the Thiessen simulation suite, which implements a better description of ionization. With that, we could probably secure this machine. And then using a similar model like TNG and extending to higher dimension.
Please, go ahead.
On a related point, do you think that local ionizing sources in the low redshift universe would play a role in these numbers? So like TNG doesn't have radiative transfer, but if you added post-processing radiative transfer to calculate like what the true ionization fractions would be from the stars, would that make a change?
I expect there to be a little change, especially also if you go to higher resolution simulations. It seems the TNG is somewhat, especially for the host regime, under-predicting, but we should expect. But this, in terms of this curve I'm showing here, will always push the blue curve further down. So the discrepancy will get bigger instead of smaller. Same holds if you use a bigger simulation speed where you have more master skeleton, will also push the curve further down.
Any other comments, questions? Looks like everything was clear. You did a fantastic job, Brian.
Great, I can start. Am I audible? Okay, great. So thank you for having me here. My name is Chiti, and I'm a Brinson Prize Fellow at Stanford University. And today I'll be talking about a new survey program that I'm leading called the DECam Magic Survey. It stands for Mapping the Ancient Galaxy in Calcium HK. And what we're doing is we're using a new narrowband filter in the dark energy camera to image a quarter of the southern hemisphere to systematically map the ancient stellar distribution populations in the Milky Way and its dwarf galaxies to understand its early evolution. So this work I'm doing with a number of co-investigators. It's a large program, and I'm excited to present the first set of results from this program here at this talk. So to take a big step back and just frame frame the conversation scientifically. So in lambda CDM, galaxies form via the merging of smaller structures. So the first galaxies to form were small, and then they merged together to form progressively larger systems. And just to highlight this fact, this is a clip from the Caterpillar suite, dark matter-only simulations, that shows the formation of a Milky Way mass galaxy. And the main takeaway that I just want you to gain from this is that as time goes forward, smaller systems are progressively merging into the central larger galaxy and building up its mass, until at z equals 0 or t equals 0, which is the present day, we end up with a Milky Way mass galaxy that's still surrounded by many other smaller galaxies that are falling in and building up its mass. Observationally, if we look around us today, this is actually qualitatively what we see. So we see that the Milky Way is surrounded by dozens of tiny dwarf galaxies, a number of substructures that correspond to the structures that you saw in the simulation that were falling in and building up its mass. And so one of the motivating questions for studying the ancient stellar populations in the Milky Way and mapping out substructure is, one, by studying these small-scale systems, we can learn something about the evolution of early galaxies, because galaxy formation proceeds from the bottom up. And two, by studying substructure in the Milky Way, we can learn something about its dark matter content. We can learn something about the dark matter content of these small-scale systems. We can also trace the formation and assembly of our own galaxy. But we can actually go a step further than this. So one thing that's beneficial about looking at systems that are around our own galaxy is that we can resolve individual stars in these systems. And the reason this is beneficial is that, remarkably, to first order, stars preserve the chemistry from the gas cloud from which they formed. This is actually very useful because if you find stars that are 12 to 13 billion years old and derive their chemical compositions, you can trace the chemical composition of the very high redshift interstellar medium in great detail. And just this is a quick schematic that just highlights this fact. So let's say you have early star formation, which begins the process of producing heavy elements in the universe. Those early stars explode and then expel their heavy elements into the interstellar medium, and then subsequent generations of stars form enriched by these metals. This process continues for 13 billion years until the present day. But if you catch stars that formed right after the initial generation of star formation, you can use their chemical compositions to trace the products of the first supernovae and indirectly infer the properties of the first stars. These stars are known as ultra-metal poor stars, or the lowest metallicity stars, because they have trace amounts of heavy elements, because they preserve enrichment from order few enrichment events. You all are probably familiar with the concept of a metallicity, but the part that I want to highlight is that when you get to metallicities below the -4 regime, there are theoretical reasons and observational reasons to believe that you're tracing enrichment by order few supernovae. So by finding these lowest metallicity stars, you can probe enrichment by individual high redshift supernovae and trace the products of the first stars in great detail. And so these are a very powerful tool for understanding sort of early chemical evolution. However, these are extremely rare. There's only about 40 stars known below a metallicity of -4, and there are actually no stars known in this metallicity regime that purely preserve population 3 enrichment or first star enrichment in the smallest dwarf galaxies. So there's a huge amount of discovery space in terms of finding these lowest metallicity stars across environments and in the Milky Way to see what enrichment by POP3 supernovae might have looked like in different environments. So all of this, mapping substructure, dwarf galaxies, lowest metallicity stars, was the motivation for the DECam MAGIC survey. So MAGIC is a 54-night program on the dark energy camera. So we've been allocated 54 nights from fall 2023 to fall 2026 to image this yellow region down here, which is basically a quarter of the southern hemisphere, spanning a number of dwarf galaxies and the Magellanic Clouds, with this narrowband filter up here, which is centered at 3950 angstroms. And what the primary science goal that we're hoping to do with this photometry is to basically combine this with existing broadband photometric data to derive metallicities of stars in a homogeneous manner across this entire footprint, basically down to the limit of Gaia proper motions. And what this will provide is basically a data set of metallicities of stars effectively 2 magnitudes fainter than existing narrowband surveys in the southern hemisphere, and provide metallicity information for stars in this huge region of the sky that one can use to look for substructure, co-moving stars at localized metallicities, and the science cases before. We have collected about 60% of our footprint so far, so we have about 3,000 square degrees. And there are a number of early science results that I want to discuss here that will be of interest. And our first data release will happen next year. Keep on pressing this. Okay, so just to highlight the power that this imaging can do in terms of studying faint, ancient stellar populations in the Milky Way, these are stars in the vicinity of one dwarf galaxy, Picture 2, which has a stellar mass of just 2,000. And it's thought that Picture 2 is likely an analog of one of the earliest small-scale structures to have formed. And the blue data points are stars with Gaia-proper motions consistent with the motion of this galaxy. We have metallicities for all of these stars now because we have imaging data. And if you apply a metallicity cut, this is what happens. So a number of the stars disappear, and the faint dwarf galaxy pops out. And there's clearly a localized overdensity that corresponds to the system, and a handful of stars in the outskirts that are potentially members of the galaxy. One thing that's exciting is, again, because we have metallicities for everything, I knew that this star, let me see if this works, was the lowest metallicity star in our data set in any dwarf galaxy that we'd observed so far. We got 10 hours of X-shooter spectra on it, and indeed, it's actually the lowest metallicity star in any ultra-faint dwarf galaxy discovered. It only has an upper limit on the iron abundance of minus 4.6, so nearly 5 orders of magnitude below what's seen in the sun. And the only two elements that we detect in the star are calcium and carbon. Calcium at extremely trace amounts, the minus 5 level, and carbon at an extremely enhanced level. And this is the first star that unambiguously preserves enrichment by POP3 supernovae in a primordial small-scale system. And we see an extreme carbon enhancement in the star that basically demonstrates that this is one pathway by which the first supernovae may have enriched primordial small-scale structures. This is just a plot that illustrates this relative to other Milky Way halo stars and other dwarf galaxy stars. So it's very exciting. We were able to fish this out because of our data. Another thing we can do is, as I showed in the last slide, because of these metallicities, we can identify pure samples of stars that belong to metal-poor substructures in the Milky Way halo and trace their morphology. So there's one particular dwarf galaxy called Crater 2, and this is work led by Kaya Atzberger, who's a grad student at UVA. So this dwarf galaxy is extremely puffy, and it's been an open question why this system is puffy. With the imaging, and if you do a metallicity selection, the blue data points are actual results from the selection, the purple data points. And the blue data points are predictions from an n-body disruption model of the galaxy. And what you notice is there's a clear recovery of stars along the direction of the n-body model, and the surface brightness of this corresponds to something like 35 magnitudes per arcsecond, and it's a clear recovery of what we're seeing. And you can use this to kind of map out the width of the stream and other observables to map out potentially what dark matter profile Crater 2 had, core cusp, and so on. This is something we're excited about too. And then finally, this is a survey. So we're covering a quarter of the southern hemisphere, and we've covered about 60% of our final footprint so far. And we can cross-match these metallicities that we're deriving for stars with distance estimates to create maps of the Milky Way. So in particular, this is work led by Alice Luna, who's a grad student at UChicago. And if you cross-match our metallicities with Gaia parallax distances and plot it in cylindrical coordinates, you clearly recover the Milky Way disk, fading into the inner halo as you go to higher heights above and below the disk plane in this resolved metallicity space. But you can actually go a bit better than this. So as Vedant and folks in the H3 survey have shown, you can use Gaia parallaxes to discriminate between dwarf and giant stars. And now, since we have metallicities, we can pick which isochrone to match the giants to get a more precise distance. And I won't go into the details, but it's extremely preliminary. But you can do this down to about 19th magnitude and then throw the distances you get into this metallicity map. And don't read too much into the result of this because we're working through the systematics, but you get the biggest metallicity map of the Milky Way made so far. In particular, we're able to derive metallicities reliably out to about 150 kpc. And we recovered known structures, substructures at large distances from the center of the galaxy. So in particular, this blob here is the LMC. We recovered at roughly the right location. If you squint, you'll see an underdensity up here that corresponds to the Sculptor dwarf galaxy. Another mark here that corresponds to the Sextans dwarf galaxy. And this is just a reddening systematic from the SMC that we're working through. But we're very excited to see what we can do with this data set to compare to SIMS and models of the Milky Way's formation. And so it's great timing because it takes me to my takeaway slide. So I presented some early science results from the survey that really demonstrate the discoveries that are possible. Again, we'll be having public data releases starting next year. And I'm happy to answer any questions about what folks might have. Thanks.
necessarily connected to an existing galaxy because the galaxy was destroyed.
Yeah.
Do you see anything like that?
I've been doing a visual blind search for streams by doing a mental SD cut and looking for clustering and proper motions. And effectively, we haven't done this systematically, but we've basically just managed to recover, known streams so far. But I'm sure this can be optimized in some way, and we're working on that.
Ramesh, and then
Yeah, mine is a dumb question. Why use calcium, H and K? Why not some other line? What's special about this guy?
Yeah, great question. So actually, it's the most prominent metal absorption line in stars.
Just because it's bright.
Just because it's, the flux dip is significant.
That's it, okay.
Yeah, so it's easy to put a narrowband on it that's wide enough that, it's instrumentally feasible to design a filter that's wide and still get signal.
Okay.
Yeah.
And typically the stars you're looking at are what? K stars?
So typically, giants are where the metal SDs work the best in. Effective temperatures from 5,500 to, from 4,000 to about 6,000 Kelvin.
Okay.
okay,
Yeah.
another question here.
So about the star you found, are you able to put any constraint on the oxygen on this?
Yeah, great question. Unfortunately, the star is a G of 20.3, so we would need an extremely large telescope to put an oxygen constraint. Just because the abundance is going to be so low, and they'll need to have at least, I think, a resolution of 10,000, and this was 10 hours on X-Shooter, so we weren't able to get a reasonable
You
oxygen.
don't need to wait too much. When is the European Extremely Large Telescope supposed to be? 5 years?
They don't have a high-res spectrograph.
Oh, they don't have?
Chiti.
Oh, they don't have? I see. Okay, so you will have to wait more. Any other comments? Let's thank Anirudh.
Isabel Sands. I'm a final year PhD candidate at Caltech. I'm part of the Feedback in Realistic Environments collaboration, and I'd like to thank the organizers for having me. Really excited to be here. And I'll be talking about some recent work I've led in which we've used the first spectral MHD cosmic ray simulations to model diffuse gamma ray emission in Milky Way-like galaxies. So there's a growing body of evidence, both theoretical and observational, that cosmic rays play an important role in galaxy formation. And gamma rays are a good probe of these cosmic ray interactions because the bulk of diffuse galactic gamma ray emission is produced when cosmic rays interact with the interstellar medium. From gamma rays, we can probe these cosmic ray interactions and constrain cosmic ray transport models. We can study feedback processes and the growth of galactic outflows, like the Fermi bubbles, which are shown here in purple. And we can search for signatures of novel physics, like annihilating or decaying dark matter. And in the past, galactic diffuse emission was studied using phenomenological cosmic ray codes like Galprop or Dragon, which are static solvers. They're unable to tell you anything about the time evolution of this gamma ray emission. But with a simulation, you can evolve all these self-consistently and determine how this emission is related to astrophysical processes. Yeah, so the specific observational motivation for this project is twofold. The first is that there's an excess of GeV gamma rays detected in the galactic center. This excess is potentially consistent with an annihilating WIMP dark matter, but it's also been argued that it could arise from a population of, for instance, unresolved millisecond pulsars. The second is the Fermi bubbles themselves, which, again, the origins are debated. They could have arisen from past activity of the Milky Way's supermassive black hole, or they could have arisen from stellar feedback from supernovae. So there's the Fermi bubbles and the X-ray counterpart, the Rosetta bubbles. Yeah, so I will talk about each of these observations and the new insights that my work has led to for each of them. So we have a set of 3 simulations that were simulated with multi-species cosmic ray spectra in multiple energy bins from MEV to TeV energies. And these include electrons, protons, their antiparticles, as well as some heavier nuclei. And in previous work, these simulations were shown to reproduce local ISM constraints on cosmic ray properties as well. Don't want to spend huge amount of time on the numerics, but I'm happy to talk about that later. So I used the cosmic ray spectra to reconstruct the 3 most important gamma ray emitting processes. The first is when a cosmic ray proton hits another nucleon in the interstellar medium, produces a neutral pion, which decays into a pair of gamma rays. And that gets you this characteristic bump in the spectrum from the pion decay. Second is relativistic Bremsstrahlung, and the third is inverse Compton scattering. The pion decay and the Bremsstrahlung are proportionate to the gas density in the simulation, and the inverse Compton is a function of the radiation field. And what I've shown here is spread in each of these values over the spread of snapshots in our simulation. This is a controlled restart. It's very expensive to run the simulations with multiple cosmic rays. So we have these over the last 450 million years of the simulation. And so right now, all of the diffuse gamma ray emission that I'm modeling is coming from these cosmic ray interactions. We're not assuming any pulsar injection. There's no AGN in these simulations, and we're not modeling any annihilating dark matter yet. So this is what the galactic center gamma ray flux maps look like. As we expect, the pion decay and the Bremsstrahlung trace the gas, which is mostly within the galactic disk. This is from the perspective of an observer 8 kiloparsecs from the galactic center. But then the inverse Compton is doing something interesting. You have this kind of biconical outflow, which I will come back to in a second. Yep, there we go. So we can compare our simulated spectrum in the galactic center to that measured by Fermi-Lat. Overall, we have a higher star formation rate in the galactic center of our simulations, which means more cosmic rays, more sources, and therefore more gamma ray flux. So here I've integrated over flux to normalize it so we can compare the spectrum shape. And it's a pretty close match. The slope of the high energy tail is a pretty good match. The peak is slightly shifted, and that's likely due to choices that were made in the original simulations that we plan to change going forward. But yeah, overall, these spectra are highly variable in shape and amplitude over time. So this is a set of, on your right, spread of snapshots over the last 10 million years. And you can kind of see that they bounce up and down somewhat stochastically. And there's maybe a factor of a few variation at lower energies and order of magnitude at higher energies. I also show variation in the gamma ray spectrum from different viewing angles within the galactic disk. Those are less important unless there happens to be some cloud of gas in the way, which does happen in M12F, the green galaxy. just kind of underlines the importance of making sure you know the distance of your gamma ray emission and are able to exclude things that are not in the galactic center. And what drives all this variation is ISM properties. The radiation field, the cosmic ray pressure, the magnetic field, and these are all dynamical properties that are mutually correlated and dependent on the star formation rate. And they vary in both space and time. So what does all this mean for the detected excess of gamma rays in the galactic center? So we have, here I've taken normalized gamma ray spectra, taken the time median spectrum and compared the spectrum at each of these snapshots to that median. And you get bumps that are somewhat similar to the 1 to 10 GeV excess detected by Fermilab. And this is just coming from time-varying diffuse emission from stellar sources. We just as easily could have happened to have seen something like this teal line at the bottom, where Galprop would have fit to this flat line at higher energies, and then instead of a 1 to 10 GeV excess, we would have had a sub-GeV excess. It's kind of a look elsewhere effect. In terms of spatial distribution, there are instances where you clearly have, this is again comparing to a time-averaged flux map. There are instances where you have an excess in 10 GeV emission that isn't there at 0.1 GeV emission. And it tends to be compact and somewhat spherical, but it's also dependent on wherever the last supernova went off within the galactic disk. So beyond the galactic center, as I alluded to before, we get features that are morphologically very similar to the Fermi bubbles. They seem to be ubiquitous in all of the galaxies in our sample. There are no AGN in these simulations. This is all coming from supernova feedback and stellar winds. And we can specifically show that the process that creates the bubbles is inverse Compton scattering. The pion decay, the Bremsstrahlung, as I mentioned before, is confined to the disk. Moreover, we can show that this is linked to a galactic fountain cycle. So around 500 million years ago in this simulation, there was a massive starburst and a bunch of gas was ejected from the galactic center. It's supported by cosmic ray pressure and kind of hanging out in the circumgalactic medium. So when we start out, we have this lepton-dominated spectrum. It's kind of arched and flatter. And then when the gas starts to fall back into the disk, you get the characteristic pion decay bump that comes from cosmic ray protons interacting with the gas falling back into the disk. It's also, the spectrum increases, so the bubbles are slightly brighter when this happens. Eventually, that gas settles back into the disk. The hadrons lose energy, and only the leptonic cosmic rays are remaining, and you return to this leptonic spectrum. I'll finish up. So the gas compresses the gas that's already in the disk, triggers more star formation, and a few tens of millions of years later, you have a new starburst and another hadronic spectrum. And so we can show that there's this black line here, that's the Fermi bubble spectrum. And those snapshots that are most consistent with that spectrum are leptonic. So the Fermi bubbles in this scenario would be the leptonic phase of this galactic fountain flow. Yeah, and we also did some modeling of other wavelengths. There's kind of a diffuse X-ray halo, as well as a synchrotron component associated with these cosmic rays. We don't see anything as clean as the Rosita bubbles, which indicates that AGN may be more involved in the creation of the Rosita bubbles. So I'll leave my takeaways here. Yeah, thank you.
Press release by some particle astrophysicists claiming they assign a 50% chance that there is evidence for dark matter annihilation in the Milky Way center. And what's your take? Is it really needed, or we can do everything astrophysically?
Well, that's what I want to figure out going into a postdoc. I think that it's very difficult to say that the excess is due to anything, either pulsars or dark matter, without properly modeling the cosmic ray transport. And I'm not convinced that existing codes do that well. Is this the Joseph Silk paper?
Maybe, yeah.
Yeah. I do think they made a really interesting point about the dark matter halo not necessarily producing spherical annihilation. Yeah, I think that's a point that had gone underappreciated, but also makes the challenge of now separating sources of the galactic center excess much more challenging.
Because if they are right, then Cumrun is wrong. Gravitons cannot annihilate. Anyway, but Cumrun is not here. So.
I should also mention one of the other things I work on is dark fit forces.
Oh.
So I'm fully agnostic.
Well, let's rule out string theory. Any other comments, questions? Yes?
Awesome talk. So these fluctuations in the gamma rays in the center, are they simulations driven mainly by amount of gas or cosmic ray fluxes?
It's mostly driven by, are you talking about the galactic center spectrum?
Yeah.
That's mostly driven by star formation rate.
But it's like because of the high frequency rate, there's more cosmic rays?
Yeah, yeah.
You need more gas to report most of it.
Both, they're mutually correlated. Yeah.
So I was wondering also, did you compare it like the fluctuations of the gamma rays with the changes in depletion time? Because there are also indications that the Milky Way depletion times in the center are large. So essentially, star formations and depletion, there's too much gas for a given amount of star formation. So maybe
Yeah, I mean, yeah, we know that the star formation rate in the center of these simulations is a bit high.
But I guess
yeah.
the question is how it compares like, to the amount of gas. So if you have more gas, then you also produce more gamma rays.
Yeah, we would. Yeah.
Okay, no more questions. Happy Thanksgiving to everyone, and thank you to all the speakers.
My eyes don't adapt that quickly.
Isabel, do you know where you're going next? Or? Okay, if you have a question.
Sure. Hi, how you doing?
That was awesome. I part of the Fermi collaboration, etc. So
Yeah.
I never even suspected that it could have been completely astrophysical due to just the gas falling back.
I mean, I'm still, so what I want to do next is put AGN and pulsars in these simulations
Sure.
and figure out what's most consistent. But yeah.
Well, that would have been my question, but I
Yeah.
figured everyone was tired.
Yeah.
So yeah, I wonder what AGN is going to tell you, whether that it explains the Rosita stuff, because that was my question before your final slide.